Hey guys, it's Tony, and today I'm going to give you a tour underneath the hood of our prototype model, the Herschel Prism, which I've nicknamed after William Herschel, the discoverer of the infrared spectrum of light. Now the reason for that is this does use infrared light to give you a range here through this sensor of the artist's hand above and below the instrument. And now if you can look on the computer, I've zoomed in here to the Ableton program, and you can see I'm actually causing the effects that program is using to create sound effects, and we can actually map those controls to any CC continuous controller knobs in the program so that range can actually change the pitch, tempo, pretty much infinite possibilities on its control mechanisms. So what it does from these sensors, I'll take you literally underneath the model here. As you've seen already, we've got our laser rangefinders that send by sending us an analog signal from the sensor, which is received by two different systems here. A stack of Arduino and Shields here, as well as the Brain Junior, which is converting to the MIDI signal that Ableton sees. So the rangefinder sends to the MIDI converter, sends over to USB to Ableton, and then we actually can get our programmable sound effects and controls for the range and note on off, depending if we're in front of the sensor or not. It also sends it to the Arduino stack, which converts some of that incoming data to color wheels and different hue patterns that is used on the top of the model to create this effect of a decay of light of what you have already played, and it maps the color based on the distance to that spectrum. From there, in that chip, it sends it out to those LED strips. We're using the fast LED I/O library files that MIT has been gracious enough to share with the public, and in spirit of that, we will be sharing everything that we create as well. From here, it also has a DMX shield on top that does a conversion of that information over to the DMX protocol, which is needed and sent back to the pin spots, which are built in here as well. And those pin spots give us that effect of a beam at a distance. You can also see here on top of the Arduino just a little bit of a diagnostic LED that gives us an indication that that is receiving good information from the sensors. Now that we've showed you how this works on a proof of concept prototype, I want to tell you a little bit about why it's not working, and it has a lot to do with the sensor quality, which is the reason that we need some help getting the quality level of the sensors and components that we believe are necessary to pull this off in a concert environment. So one of the biggest problems I noticed right off the bat is that we do get a lot of electrical interference across the sensor lines. It could be caused by a number of factors that right now cause the sensors to send a lot of erroneous data. As you can hear, it's kind of playing on its own right now. Our effects concepts of being able to see you play these beams is critical to be able to have some haze or some smoke in the environment, but as you can see, I'm getting a lot of misfires into the fog. It's thinking that my hand is over the top of it now. As it sees the fog and its own reflection, basically, the infrared light is scattering and scattering back to the sensor due to this haze in the air. That's why we need the really high quality industrial grade laser rangefinders that are excellent at particle rejection, so they're going to be able to cut through that smoke and give us the true accurate reading of where your hand is over the top. That's just not capable with an infrared sensor. And there you have it. That's the quick rundown of how our proof of concept prototype has operated and works in the code and physical environment. We're really excited to try this next iteration with the high quality sensors we need to really prove that this concept can work in a concert and theater environment. Thanks for watching, guys. Have a good rest of your night.